Hello friends, welcome to Mechanical Engineering online classes. Today's lecture will be delivered by Miss Shravani Sriramoju.
Let us learn how to solve a minimization type LPP by Simplex method. So, because we have already learned how to solve a max type of problem in the previous video, I shall solve this in two methods. One is a method that you've already learned. So for that I'll convert the given objective function, which is z here, which is 8x1 minus 2x2. I will convert this z into a max type and solve. That is one method. The other method is I'll solve it keeping z as it is. Means I'm not going to change the objective from min to max. So let us get started with method 1. So in method 1, I will convert the minimization problem into a maximization problem. If the given question was a max type, then we already know how to solve the problem. We have already solved it previously. If you want to check it back, you can check it in the description. The link is given. Now here this question is a minimized type of question. And for us to understand how to convert it into a max type, then you must be knowing that minimize z is nothing but maximizing minus z, or otherwise maximizing minus z is nothing but minimizing z. So here the question is minimize z. So I can convert it into a maximize of minus z. So because z is equal to 8x1 minus 2x2, minus z will be equal to minus 8x1 plus 2x2. So let this minus z be some z prime. So we have converted the min type into a max type. So minimize z is nothing but maximize minus z, which is z prime, that is equal to minus 8x1 plus 2x2. So this is the objective function which we have rewritten. This and this are same. Now we can rewrite the question as maximize z dash is equal to this one, minus 8x1 plus 2x2, which is subjected to the given constraints are these: minus 4x1 plus 2x2 is less than or equal to 1, 5x1 minus 4x2 is less than or equal to 3, where x1 and x2 are greater than or equal to 0. These are the constraints. This is a non-negativity restriction. Now we shall write the given problem in standard form. So let us first write the constraints: minus 4x1 plus 2x2 plus s1 is equal to 1, 5x1 minus 4x2 plus 0 into s1 plus s2 is equal to 3. So let us write all the expressions in terms of all the variables. And now comes our objective function: maximize z dash is equal to minus 8x1 plus 2x2 plus 0 into s1 plus 0 into s2 for all x1, x2, s1, s2 being greater than or equal to 0. So this is the standard form. Now that the standard form is ready, we know that Simplex starts with finding the initial basic feasible solution. We already know what a basic feasible solution is, what a feasible solution is, and what a basic solution. If you do not know, there's a video on it again. You can check it back, or the link is provided in the description. You can check through that also. Now IVFS means we have two constraints and 4 variables, so I can find only 2 variables at a time. And for it to be feasible, for the solution to be feasible, this non-negativity restriction must be satisfied. So it is always important that whenever we start with solving a simplex problem, the first step should always be a feasible solution. If the first step is into feasibility, feasibility means something which is practically possible. So if the first step is into feasibility, then every next step comes out feasible. So for that reason, the first assumption is that let x1 and x2 be equal to 0. Because x1 and x2 are the decision variables, the minimum value that it can take is 0. So I have decided not to produce any product. That also can be a decision. So we are starting with that basic and first stage of decision, that right now we have decided not to produce any product, not product A, not product B, nothing. Now for given x1, x2 values as zeros, these we have made non-basic variables, right? Then what are the corresponding values of s1 and s2? Substitute x1 as 0 here and x2 as 0 here, you will find s1 as 1, and if you substitute x1 and x2 zeros in second constraint, then you get s2 as 3. So this 1 and 3 are satisfying these two conditions because they are the outcomes of from the 1 and 2 equations only. And not just that, our x1, x2, s1, s2, all of them are satisfying this non-negativity restriction as well. So therefore this is an IBFS. So what is z dash now? We know the value of x1, x2, s1, s2. x1, x2 are assumed to be zeros. s1, s2 are found as 1 and 3 respectively. So therefore our z dash will be minus 8 into 0 plus 2 into 0 plus 0 into 1 plus 0 into 3, which is 0. So we have obtained an IBFS for our simplex. So our table 1 can be now ready. So we'll write Cj, Cb is the coefficient of basic variable in Z, Bb is the basic variable. Then let us take down all the variables that are there. Cj means the coefficients of x1, x2, s1, s2 in Z, which is nothing but minus 8, 2, 0, 0, these things. So let us note them down here. Now, what are the basic variables? We have made these non-basic variables. So we have found these. So whatever we have found are the basic variables, s1 and s2. Their coefficients in z or z dash is 0. 0 and 0. Now let us note down the constraints here. What are the constraints? The given constraints are minus 4x1 plus 2x2 plus s1 plus 0 into s2 equal to 1. Let us write down all those coefficients here. Minus 4x1 plus 2 for x2, s1 is 1, s2 is 0, p is 1. Similarly, the second constraint, s2 belongs to second constraint, right? So we'll write second constraint here. 5 minus 4, 0 and 1. This is equal to 3. Now how do we find z? Z dash is nothing but sigma cb into aij, means 0 into minus 4 plus 0 into 5 is 0. Similarly 0 into plus 2 plus 0 into minus 4 is 0. The same way all these have come out to be 0. So here also it is 0 into 1 plus this 0 into 3 is 0. So this is the value of z. So from first table we can straight away read our IBFS. What is IBFS? x1 and x2 are zeros. Here they are not part of basic variable set, so they are obviously 0. S1 is equal to 1, we can read it here, S1 is equal to 1, S2 is equal to 3, and therefore the corresponding Z dash is equal to 0, which is this. Now all that we have to do is to check whether the obtained solution, so far the obtained solution which is Z dash is equal to 0 is the best solution or not, or can we improve it. So for that we will be calculating the net evaluation row or index row as Cj minus Zj dash. Cj is minus 8, Zj is 0, so this is minus 8, so 2 minus 0 is 2, 0 minus 0 is 0, 0 minus 0 is 0. And now from the condition of optimality we know that our Cj minus Zj dash is considered to have attained an optimum solution when this NER is all zeros and positives, zeros and negatives for a max type of problem. So if you haven't checked out our previous video on the optimality conditions and feasibility conditions for simplex method, you can check it back in the playlist, it's there, or the link is provided in the description. So from the optimality condition, it can be seen that the solution can be improved. How can we improve the solution? Because it's a max type of problem. For a maximized type, a positive number can increase or improve the problem. For a min type, a negative number can improve the problem, improve the z. So here there is a positive value. Out of -8, 2, 0 and 0, there is a positive value 2 which is corresponding to x2 variable. So now x2 variable is the entering variable. Now that because we can find only two variables at a time because we have only two constraints, we have to kick out one of these basic variables. Which variable must be kicked off? We have to find replacement ratio or minimum ratio in order to decide whether to make S1 a leaving variable or S2 a leaving variable. How do we find that? It is B divided by corresponding pivot column coefficient. So for S1 it is 1 divided by 2, and for S2 it is 3 divided by -4. So we have to pick the minimum non-negative as a leaving variable. Now the leaving variable is known, we also know the entering variable. So as we could see that there is an entering variable, there is always a chance of improved z. Now let us see. So as we know that the simplex algorithm always tries that at every table we can read the values of basic variables without any further calculation, and we can also straight away read the value of corresponding z. Alright, so what algorithm or what logic helps us read the value of S1 straight away, the value of S2 straight away? In this first table, just look at it. If you write this down, it is -4 into x1 plus 2 into x2 plus 1 into s1 plus 0 into s2 is equal to 1. Because x1 and x2 are not a part of basic variables, these values are zeros. And the coefficient of s1 is 1, so it is 1 into this s1 plus 0 into this s2, this s2 is equal to 1. So everything else has become 0. It is straight away s1 is equal to 1. Similarly, if you check with this second constraint, straight away you can read 0 into s1 plus s2. 0 into s1 has a value which is 1, but s1 is not calculated here. So there is no computation time required for so many calculations. We are not solving it as a simultaneous equations. Straight away you can read s2 as 3, and that became possible only because the basic variable set, which is here, for example the first table, which is s1 s2, are an identity matrix. If you check this, s1 to s1 is 1, which is this, s1 to s2 is 0, this one. Similarly, s2 to s1 is 0 and s2 to s1 is 1. So this is the reason why we use Gauss-Jordan method in order to rewrite the constraints without actually changing their meaning. So what should that mean? Now our basic variable set is changed. So our basic variables comprise of x2 in place of s1. So this is x2 and s2 is as it is. So we will change only one variable at a time. We are going to pick only one entering variable. Here in this particular first table there is only one positive number. But even if there are two numbers, like we have seen in the previous problem of max type, there were two positive numbers, but we have picked only the most positive. So we'll pick only one entering variable, one at a time. We don't play with multiple variables at a time. So here in place of s1 comes x2 and s2 is remaining as it is. The coefficient of x2 in z in the objective function z dash is, for s2 it is 0. Now how are we going to write these constraints in such that the basic variable set x2 s2 is becoming an identity matrix? Let us see this. So that means this should become 1, this should become 0, this becomes 0, and this becomes 1. This should be the identity matrix. And now, in order to make this happen, I've given already the formulas on how to write the rows, the entering variable row or the other rows in a previous example. So entering variable row is nothing but leaving variable row divided by the key element. Key element here is 2. So divide every element of S1 by this 2 and we will get x2 row. So minus 4 by 2 is minus 2. 2 by 2 is 1. So we attained this. Now 1 by 2 is this. Then 0 by 2 is 0. We got this also. This is nothing but 1 by 2. If you see, for the leaving variable, RR will become the entering variable's B value. So that's the reason resources are always supposed to be 0 or positive. It cannot be negative. That's the reason why we pick only minimum non-negative variable here. Minimum non-negative ratio as the leaving variable here, because that value can be seen here. So this value appears here. Now let us write S2. So new S2 is equal to old S2 minus its pivot column coefficient multiplied by entering variable row. So that is nothing but previous old S2 is 5. 5 minus its pivot column coefficient is, pivot column is this one, x21, which is minus 4. So minus of minus 4 into, what is x2 there? x2, corresponding x2 is minus 2. So this will become 5 minus 8, which is minus 3. So we can write it here. And similarly, this value, let us see whether we get 0 or not. It should be minus 4 minus of minus 4 into 1. So minus 4 plus 4 is 0. So this is 0. So this 0 minus of minus 4. Its corresponding pivot column coefficient won't change, right? This minus 4 into this 1 by 2. This is equal to 4 by 2, which is 2. So this is 2. And now how do we get this value? It is 1, this 1 minus 4 into this 0 is equal to 1. For a clear understanding, I have written the formula. New S2 is equal to old S2 minus its pivot column coefficient. Its pivot column is entering variable column. Its pivot column coefficient is a corresponding one. Corresponding to S2 is minus 4 in that entering variable column. So this value is minus 4, which is shown here. This value must be multiplied by entering variable row, which is nothing but our x2 row. So old S2 is this 5 minus 4 0 1 3, this one 5 minus 4 0 1 3 minus of its pivot column coefficient is this minus 4 multiplied by entering variable row. Entering variable row is this x2 row. Minus 2 1 half 0 half, this is there, no, that is the entering variable row. And now solve this. Corresponding elements must be added. Now 5 minus of minus 4 is plus 4. Plus 4 into minus 2 is minus 8. 5 minus 8 is minus 3, which is written here. Minus 4 plus this 4 is this one, which is 0. Similarly 0 plus 4 by 2 is 2, which is this one. Now 1 plus 0 is 1, which is this. And under B it is 3 plus 4 into 1 by 2. So 3 plus 2 is 5, this one. which is here. This is 5. So the value of x2 is 1 by 2. The value of s2 is 5. So we can straight away read the values there. Now let us find z dash as sigma cb into aij. So 2 into minus 2 plus 0 into minus 3 is minus 4. 2 into 1 plus 0 into 0 is 2. 2 into 1 by 2 is 1 plus 0 into 2 is 0. So this is 1. Similarly, this comes out to be 0, and this is 2 into 1 by 2 plus 0 into 5. That is nothing but 1. So the value of z dash is improved. We got this as 1. Previously it was 0, and for a maximized problem it is improved to 1. Now let us see if this is the best solution. If the best answer cj minus zj dash is minus 8 minus of minus 4 is minus 4. 2 minus 2 is 0. This is minus 1. This is 0. So if you see, the net evaluation row always gives you a 0 value for the basic variables. Even in table 1, the basic variables were s1 and s2. So cj minus z will be zeros, because they are already contributing. So there is no further contribution. So here also x2 and s2 in the second table, x2 s2 are the basic variables. So under that, our net evaluation row will show our 0 values. So for a max type of problem, the net evaluation row, if it is cj minus zj dash, is all zeros or negatives, then there is no further possibility of improving the solution. So whatever we have obtained right now is the best solution possible for the given problem. So therefore, maximize z dash is equal to 1. This means it is minimize z, which is minus 1, because z is minus z dash, or z dash is minus z. Both are same. The question was in terms of z, so we have reconverted into z. So the solution is that minimum z is minus 1 with x2 as half, s2 as 5, x1 is 0 and s1 is 0. So this is the answer by method 1, where we have converted the given problem into a maximized type. Now let us solve the same problem without converting it into a maximized type. So keeping it as a minimized type only, we have to solve the problem. Now that we don't have to convert the min problem into a max type of problem, I have straight away written the standard form. Min z is equal to 8x1 minus 2x2 subjected to minus 4x1 plus 2x2 plus s1 plus 0 into s2 equal to 1, and 5x1 minus 4x2 plus 0 s1 plus s2 is equal to 3. All the expressions are written in terms of all the variables. Now let us see the IBFS to this. Initial basic feasible solution is, it starts with an assumption that x1 and x2 are zeros. Then substitute x1 and x2 here. We straight away get, if this is 0, this is 0, this is already 0. So s1 is equal to 1. Similarly, s2 is equal to this, and these are zeros. Only s2 is left. So s2 is equal to 3. That is this. So this is the IBFS. This is also positive, this is also positive, 0 or positive. So that means they are feasible solutions. And the corresponding value of z is, this is 0, this is 0, this is made 0, this is also made 0. So z is 0. This is the IBFS. Let us start with the simplex table. Coefficients of x1, x2, s1, s2 from z is 8, minus 2, 0 and 0. Then the basic variables here in the first step, IBFS is s1 and s2. This is s1, s2. Coefficients of s1 and s2 in z are zeros. So what is the first constraint? Anyway, S1, S2, they are making an identity matrix. You can see it here. So it is minus 4, 2, 1, 0, 1. This is 5, minus 4, 0, 1 and 3. Now find Zj as sigma Cb into Aij. So you have 0 into minus 4 plus 0 into 5, that is 0. 0 into 2 plus 0 into minus 4 is 0. Similarly, everything is 0. This is 0. So this is what we have seen here. Now let us see if this is the best solution. NER is Cj minus Zj. Cj is 8. 8 minus 0 is 8. Minus 2 minus 0 is minus 2. So 0 and 0. So in the previous case, for a max type of problem, we have picked the most positive value as the entering variable. This is most positive in this. The corresponding variable is chosen to be the entering variable, because the positive value will contribute in increasing the value. For maximization, we are taking the most positive value. Now, when the case is minimized type, most negative value will reduce the value. So if we want to increase the value, then we are picking the positive value, that is for max type. If you want to decrease the value, you have to take a negative number only. So this is a min type of problem. So we have to pick the most negative value of Cj minus Zj as entering variable. So that is corresponding to x2. So x2 is the entering variable and its column is the key column or pivot column. Once, because we could find there is a variable that can contribute to our objective, there is a possibility of improving the solution. So when there is a possibility of improving a solution, this is not the best answer. The 0, z being 0 is not the best answer. So if x2 has to enter, what should leave? We have to find the minimum ratio now as b by corresponding pivot column coefficient. So it is 1 divided by 2 here. This is 2. This is 1 by 2. Then for S2 it is b divided by this minus 4. That is 3 by minus 4. So whether it is a min type of problem or max type of problem, finding the leaving variable is having the same criteria. Unlike finding the entering variable. Finding entering variable is for min type it should be most negative. For a max type it should be most positive. Alright, but for a leaving variable, whether it is max type or min type, we have to pick the minimum non-negative. So here also we are going to pick the minimum non-negative as leaving variable, which is S1. So the intersection of S1 and X2. X2 is a pivot column or key column. S1 row is a pivot row or key row. The intersection of those is a pivot element or key element. Here it is 2. Now once we know what is entering variable and leaving variable and the key element, we are now all set to write the modified simplex table. What are the basic variables here? In place of S1 comes X2. S2 is as it is. Coefficient of X2 in Z is minus 2. S2 is 0. Now how do we write the entering variable row, which is X2 row? I told you it should come X2 S2 variable set should be an identity matrix. So this is nothing but S1 row by key element, which is 2. So writing the constraints, it is all the same for max type or min type. The only change is with Z. Z is becoming minus Z if you are converting it from max to min or min to max. Rest all things are same. So S1 is divided by 2. Now this is our X2 row. And S2 row, how do we do it? We have already done here. X2 row, new S2 row is equal to old S2 minus its pivot column coefficient into entering variable row. What did we get? Minus 3, 0, 2, 1, 5. We will get the same here also. Minus 3, 0, 2, 1 and 5. Now once this is all there, we can find Zj as sigma x cb into aij. Minus 2 into minus 2 is 4, plus 0 into minus 3, this is 4, this is minus 2, this is minus 1, this is 0, now this is minus 1. Alright, so this is the value of z when x2 is equal to half and s2 is equal to 5. If you want, we can check it back with these given constraints. Just see, x2 is equal to 1 by 2, right? x2 is equal to 1 by 2 and s2 is equal to 5. Substitute these values in z, you will get the answer for z. This is 0, this is minus 2 into half is minus 1, this is 0, this is 0. So z is equal to minus 1. So for x2 and for x2 as half and s2 as 5, we have z as minus 1. We got the same here. And even before writing this table, if you want to check back, if you want to verify, what we can do here, after table 1, we have seen that the basic variables are x2 and s2, no more s1 and s2. So when basic variables are x2 and s2, that means x1 is 0 and s1 is 0. Substitute this x1 and s1 as zeros in these constraints. x1 is 0, s1 is also 0. So two equations, 2x2 is equal to 1, this is 0, right? So x2 is equal to half, that is what we have got here. Alright, then similarly you can solve this also, the second constraint. In the second constraint, if you are substituting minus 4 into x2, what is x2? We just found x2 as half, plus s2 is equal to 3. So this is minus 2. Minus 2 plus s2 is equal to 3. s2 is equal to 5. So even if you are confused with the formula anytime, anywhere, you can check back with what values you are getting here by simply substituting the corresponding non-basic variables as 0 in the given constraints. Here for this table 2, x1 and s1 are the non-basic variables. You put these as zeros in the given constraints and you find the remaining constraints, you will get the same values. Here x2 has come out to be half and s2 came out to be 5. That is what had happened here, right? These are the values. So now we have also seen how to verify our answers in the table. Alright, now let us see if we can further improve this by finding Cj minus Zj. 8 minus 4 is 4, minus 2 plus 2 is 0, this is 1, this is 0. Now here there is a difference in max and min type of problems, just like how we have checked here. Entering variable, we have to see whether there is an entering variable or not. For a minimized type of problem, if we have a negative value in our NER row, then the most negative will be chosen for entering variable, but here there is none. So optimality is attained. There is no negative value in Cj minus Zj. All are zeros or positives. So if we are entering x1 or s1, that will only increase the value of z, whereas this is a min type of problem, it should decrease. So that if it has to be decreased only when there is a negative values here. Now since all the Cj minus Zj are zeros or positives, for a min type of problem optimality is reached. So we can write the answer as, therefore minimum z is equal to minus 1 for x2 is equal to half, s2 is equal to 5, where x1 is 0 and s1 is 0. This is the answer. Whether you do it in max type or min type, you get the same answer. You check back with this. We got the same here. Min z is minus 1, x2 is half, s2 is 5, the rest x1, s1 are zeros. Here also it is the same thing. So in a similar fashion, when a max type is given, you can convert that into a min type and you can solve. Suppose z max by z is given, you can make it as minimize minus z. Let this be some z dash. Your z dash is minus z. You solve it like this in method 1. You get it? So you can solve it in any fashion, but you have to be careful when you are deciding which is an entering variable. Your entering variable is the only place where you have to choose such that it addresses the objective of the given function. Objective of the given function is whether to maximize or minimize. That's the only place where you have to be alert. Otherwise, the rest of the methodology is all same for a max type or min type, whether you convert it or not. And not just that, but I just would like to mention one point here. In some textbooks, they use Zj minus Cj also. So I'm writing it down here in order to avoid confusion. In case for a minimization type problem, in case you're following different kinds of books where Zj minus Cj is given, then the optimality condition is, suppose Cj minus Zj, it should be all zeros or positives, like here. It is all zeros or positive, so the optimality is attained. This is the optimality condition. Once this zeros or positives are attained, then the solution is considered to be optimal. Optimality is attained. In case you are using Zj minus Zj, naturally it should be all zeros or negatives for the optimality to be attained. This is the optimality condition for a min type of problem. Now for a minimized type of problem, how do we check with entering variable condition? Entering variable condition in all for a min type of problem, in case we are using the Cj minus Zj concept, say in this. What was entering variable for a min type? Cj minus Zj. If our net evaluation row is Cj minus Zj, then the most negative value, variable corresponding to most negative value of Cj minus Zj is considered to be the entering variable, right? So that is what it is. So if we are using Cj minus Zj, then you have to pick most negative Cj minus Zj as entering variable. If you are using Zj minus Cj, then it's obvious that you must pick the most positive Zj minus Cj as entering variable. So this is all for a minimized type of problem. Similarly, let us see for the max type of problem. I just suggest that you follow any one convention. I always follow Cj minus Zj alone for max type or min type or whatever it is. But I'm just, because there are several textbooks with several conventions, so I'm just trying to put them all into one shell so that you don't get confused. No matter what convention you are following, I'm just shelling it into one particular place so you can clearly follow. If Cj minus Zj is your convention, for a max type of problem, the optimality is attained when Cj minus Zj is all zeros or negatives. If Cj minus Zj row is having all zeros or negatives, like our method 1, everything is 0 or negative here. So for max type of problem, that condition declares that there is no further possibility of improvement. So that is, optimality is attained. This means that optimality is attained. In case you are someone who follows this Zj minus Cj, then this is opposite of that, zeros or positives. If it is all zeros or positives, then it means optimality is attained. And similarly for an entering variable, how do we check? If you are checking with Cj minus Zj, then for a max type of problem, the one with most positive Cj minus Zj is what is the entering variable. Most positive. Here it is most negative, right? So here it will be most positive. Most positive Cj minus Zj is considered as an entering variable. If you are someone who is following this, then it will be naturally the most negative zj minus cj is considered as the entering variable. So I have mentioned all the possible cases at one place. Hope this helps.
Thanks for watching. If this video was of help to you, please like it and share it with your friends. And don't forget to subscribe to our channel.